And we're on to lesson 4.6, which is going to be your multiplication rule for independent events and the at least one rule. We didn't really do an activity today. There's just sort of a thought project going on here. So a local news station recently added a snow day calculator and a traffic jam calculator to their website. And they've got some probabilities. We're starting out with the snow day calculator. What you're seeing in here is not a probability distribution. These numbers don't add up to 1. Every day just is assigned in a probability for having a snow day. So the first one, probability of a snow day on Thursday. Thursday is 0.7. And the interpretation of this is 70% chance of snow day on Thursday. Probability of a Friday snow day is right here, 0.6. And that would be a 60% chance of snow day on Friday. And then they go on to ask, are the events Thursday snow day and Friday snow day independent? And think about it this way. If it gets really cold one day, what about the next day? Do you have any kind of idea of whether it'll be a warm day or a cold day? Really, you can't know for sure, but in general, weather events on consecutive days can be similar. So knowing that Thursday is a snow day would increase the chances of Friday being a snow day. All right. Well, the fourth question is, they want us to calculate the probability of Thursday snow day and Friday snow day. Remember from lesson 4.5, and means to multiply. So you might think, all right, it's 0.7 times 0.6 would equal 0.42. But you would be wrong. And the reason that you would be wrong is these days are not independent. We actually have a formula, which is the probability of A and B equals the probability of A times the probability of B. Let me fix that. That looks bad. Times the probability of B. But this only when A and B are independent events. And we've already said they're not. See, we said no. So this is an inappropriate formula. We would need the probability of A and B equals the probability of A times the probability of B given A, but we don't have a conditional probability, so we're not really able to calculate this, nor are we able to use this formula. Let's move on past the stop sign and get to their traffic jam calculator for the week. And they're just, again, assigning a probability of what they think is the most likely outcome for a traffic jam on any one of these days of the week. It's not a probability distribution, again, because all those probabilities are greater than 1, but they just have the chance for each day. So the probability of a Monday traffic jam is 0.4, and that's 40% chance of a traffic jam on Monday. Friday traffic jam is over here, that's 0.7, and that would be a 70% chance of a traffic jam on Friday. So are the events Monday traffic jam and Friday traffic jam independent? those days are pretty much separated by several other days in between. So knowing that you have a traffic jam on Monday doesn't really tell you much about what's going to happen on Friday. There is, a level of argument that you can make on this, like if they're doing sort of long-term repairs and that's creating a traffic jam, there should be a traffic jam all week. But let's just go ahead and assume that these are independent, so that knowing whether or not there's a traffic jam on Monday really doesn't change the probability of a traffic jam on Friday. And for purposes of answering the remaining questions, let's just assume that traffic jams are independent events for any day. So the probability of a Monday traffic jam and a Friday traffic jam, that is going to be 0.4 times 0.7 equals 0.28. So that we can use that formula that we saw up top for the multiplication rule for independent events. Now the probability of a traffic jam every day of the week, that's just going to be the product of all five. So 0.04 times, 0.4 times 0.2 times 0.3 times 0.5 times 0.7. Okay, that's a lot of fractions, so this should give us a pretty small number, 0.0084. So it's pretty unlikely of seeing a traffic jam every day of the week. All right, the probability of no traffic jams all week, well, just think about it. If the probability of a traffic jam on Monday is 0.4, then the probability that there isn't one is going to be 0.6. And it's just the complement. So for the same for Tuesday, 1 minus 0.2 is 0.8, then 0.7, 0.5, 0.3. So I've kind of extended this table to have the probability of a traffic jam and a probability of not a traffic jam. So now we can multiply all five of those new numbers to see about the probability of no traffic jam this week. So 0.6 times 0.8 times 0.7 times 0.5 times 0.3. And again, it should be a pretty small number, 0.0504. So what is the complement of at least one traffic jam this week? Well, at least one traffic jam means that you would have maybe a traffic jam on one of the days, or two of the days, or all five of the days. The complement would be no traffic jam all week. So that would be no traffic jam. Or let's put it plural, no traffic jams all week. So what is the probability of at least one traffic jam this week? Well, this can get complicated because you could have a traffic jam on Monday and none of the other days. Or you could have one on Tuesday and none of the other days. Or Wednesday and none of the other days. You could have Monday and Tuesday would have traffic jams and not these three. Or Thursday and Friday could have traffic jams but not the first three. I mean, there's so many ways of having at least one traffic jam that you could take forever to answer this question. In order to make this easier, we want the probability of at least one traffic jam this week to equal 1 minus the probability of no traffic jams. Because that can only happen one way. I mean, we figured that out already up in problem number 10. So we can just do 1 minus 0.0054. Oh, check that. I have that number wrong. Let me fix that. 0.0504, just like in number 10, and that will be 0.9496. Moving on to page 2 with our learning targets. Learning target number 1 is to use the multiplication rule for independent events. So So let's highlight that for independent events to calculate probabilities. And here's the formula. I'll just put a little dot in between here to indicate multiplication. Learning target number 2 is to calculate the probability of at least 1 using the complement rule and the multiplication rule for independent events. So the probability of at least 1, as we saw in that last problem, at least 1 traffic jam, was 1 minus the probability of none. And then finally, learning target number 3, determine if it's appropriate to use the multiplication rule for independent events in a given setting. So use only the probability of A times the probability of B for independent events. Otherwise, use the probability of A times the probability of B given A when, let's make that an N, when events are dependent. Lesson 4, App 4.6 is about genetic screening. So here goes. The first trimester screen is a test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to a study published in the New England Journal of Medicine, approximately 5% of normal pregnancies will receive a positive result. All right, so the probability of positive equals 0.05. Therefore, the probability of negative is just the complement of that, 0.95. Assume that test results for individual women are independent. That is telling us which formula to use. That means we're going to use this guy, which is just a shortened version of this guy. Suppose that 2 unrelated women, now this is another way of saying independent, when they say the 2 women are unrelated, because if sisters go in and they're both pregnant and one gets the test and has a certain result, you can maybe project to the other one, since they're sisters, that if there's a problem, the sister may also have a problem. May not, but at least you have some knowledge that she could. That would be a lack of independence, but if they're unrelated women, that's a sign that we've got independence working. We already knew they were independent from the problem, but just so that you know. So suppose 2 unrelated women are having normal pregnancies. Devondra and Miranda are given the first trimester screen. What is the probability that Devondra gets a positive result and Miranda gets a negative result? So let's write this out. So the probability, I don't like that P. Let's start that over. Probability of Devondra positive and Miranda negative Well, since they're independent, we should be able to just multiply. Let's see, positive for Devondra would be 0.05, and negative for Miranda would be 0.95, and those two would multiply to 0.0475. Easy, easy, easy. That was quick, gave us a lot of room to write, and not really a need to use it. Now this one, number 2, this is a potential problem. So I'm going to put a little star on, a little asterisk. All right, if 100 unrelated women with normal pregnancies are tested for the first trimester screen, what is the probability that at least 1 woman will receive a positive result? All right, here we are with that at least 1 question. All right, and think about what a nightmare this would be. Maybe the first one would receive a positive and the other 99 wouldn't, or the second would receive it and the other 99 women, or the third, or the fourth, or the first 2, or the first 8, or the last 8, or the last 20, or the middle 13. I mean, there's just, you could take a year trying to get all of these individual probabilities, and they would all be ors, so you would add them up. Yeah, no. Let's just go ahead and just say the probability of at least one positive. Let's just set that equal to the probability. Let's check that. Let's say 1 minus, that's equal to 1 minus the probability that there are no positives. In other words, that all 100 women are negative, okay? If that's the only way, there's only one way that can happen. All 100 would have to be negative. If we subtract that from 1, then what's left over would be the probability of at least one positive. Okay, so let's do the probability of no positives. Isn't that going to be equal to the probability of all negative? And the probability that anybody was negative, let's just write that down just for our use, was 0.95. Okay, so this is going to be, the first is negative, and the second and the third and the fourth, all the way up to the 100th. That's going to equal 0.95, and we don't want to really write that 100 times. We're just going to go to exponents and raise this to the 100th power. So that'll be 0.00, make sure I have the right number of zeros, 59. That is the probability of all negatives. So we can write this as 1 minus, let's just say 0.95 to the 100th power, or we could write it as 1 minus the number that we found, 0.0059. Either way, we're going to get our answer is going to equal 0.9941. See how much quicker that is than trying to figure out all the different ways that you could get at least one woman with a positive result and adding them all up. There's literally thousands upon thousands of ways. But if we just subtract the other option, which there's only one way to do, that probability from 1, then we just immediately get the answer for at least one positive. So there it is. Thanks for watching. See you next time.